of our National Conclave and Policy Dialogue on Tuberculosis. I hope you had a productive first day yesterday filled with meaningful discussions and valuable insights. Yesterday, we began our deliberation with an engaging session on universal drug susceptibility testing, highlighting its pivotal role in ensuring early detection of drug resistance and guiding an appropriate and personalized treatment in tuberculosis. So today we build upon that strong foundation by turning our attention to another transformative area in tuberculosis care, that is genomic testing in tuberculosis. Advances in genomic technologies are redefining the way that we diagnose tuberculosis, detect drug resistance, and understand transmission dynamics and strengthen the surveillance. These innovations have the potential to accelerate the precision medicine in TB as well, enabling a faster, more comprehensive, and more effective patient care while supporting evidence-based public health decision making. Yet, interpretive challenges, lack of standardization pose a significant challenge to immediate scale-up of this modality. This session will enlighten us regarding the diagnostic yield, clinical validity, and utility of genomics in Mycobacterium and its integration into the clinical care. Now, I request the eminent chairpersons of the session, Padma Shri Dr. Digambar Behra Sir, Emeritus Professor in the Department of Pulmonary Medicine, PGI Chandigarh, and our Executive Director and CEO, AIMS Bhubaneswar, Dr. Ashutosh Vishwas Sir, to chair the session on genomic sequencing in Mycobacterium tuberculosis in India.
Good morning. Good morning. Welcome to this second day's session. I think this talk is very important, that we will try to understand what is actually the genomics of Mycobacterium tuberculosis and how it is going to, enrich our understanding, and how this technology is going to help in our diagnosis of the changes, the resistance, the sensitivity of the bacteria that as we are discussing yesterday. So I am sure both the experts are going to tell us very clearly, so that we will have a clear understanding about the various mechanisms, the issues associated with these genomic testings. So you have to tell something.
Good morning to all of you, and I hope today's program will be wonderful to go through all those very important topics. And today, to begin with, our very important area, that genomic and the role of genomic in the elimination of tuberculosis in our country. So there are two eminent speakers, the renowned speakers today, Dr. Anish Kumar and Dr. Dinesh Kumar. So those are very, as you can see, lot of publications are there in the molecular level. They're the best, I think, to present you to deliver about this genomic role of genomic and the technique and other things. So I hope this will be very useful session. So I request to, can we invite the speaker or you are going to speak? So now the first speaker that we are going to invite the Anish Kumar for the deliberations of the today's beginning topic. Yes, Dr. Anish Kumar.
And thank all the organizers for having us here to discuss the kind of work that we have been doing for the last 3 years. So in 2023 we started with the DBT. This is one of the flagship programs of the Department of Biotechnology. So in 2023 we started this program with a very ambitious plan to collect 32,000 TB isolates. There is no such data sets available at this point anywhere else in the world. So that is quite an ambitious aim for us to get, and we came up with a very tight group of people, and that is spread across all over India. That goes with the sample collection, sample shipment, then making a biorepository and isolating DNA sequencing and analysis. The entire workflow, like in a pipeline fashion it works. So the main institutes that are involved are JIPMER in Pondicherry. Dr. Sonali, who is here, she leads the clinical aspects of it. And then the other sites like PD Hinduja, there is BMMRC, PGA Chandigarh, BJGMC, then NITRD in Delhi, St. John's in Bangalore. Many such clinical sites are collecting samples, of course, with the help of a lot of all the state and district TB officers. And all these samples come to ICGEB, which is in Delhi. So where Dr. Dheeraj, who will be talking about it after me, so his group make sure that all are treated in the equal way, make a high quality biorepository for all the clinical isolates. I don't think anywhere it actually exists to this scale. I think most of the companies that use, there is a European one that has around probably 150, 160 samples. Now here we are talking about tens of thousands of strains. So he takes care of that, and he isolates the DNA QC, send it to CCMB in Hyderabad, NIBNG in Kalyani, Kolkata, and NII to do sequencing. And finally, at NII, we do the analysis. We have made a portal. So all this data, all this mutation data is now available, publicly available today on a web portal, which was shown yesterday. It is completely accessible for everybody, including the metadata. And the whole genome data will be accessible soon enough, the raw data. So that's what we have been doing in the last 2 years. So why do we do all these things, right? So that's the question. You're making a lot of, making a huge repository. You are getting all these sequences done. Why should we do this? What the public is going to get benefit out of it? So the main point is, we are the largest contributors to tuberculosis, and our country is affected very badly by tuberculosis, with over 3 lakh of deaths per year. It's a huge number, right? And even now, apart from the overall idea about this lineage changes here, there, other than that, we have no idea about how the genome diversity of this bacteria is spread in India. And that is extremely important, because it is this genome diversity that leads to development of drug resistance. Because that's actually now going to, we have very big problem of drug resistance, which actually makes it very difficult to treat the bacteria. So that's why we need to know how this drug resistance is evolving and how it is spread all across in India. Do we have hubs that we need to worry about? All this information to get all this information, we need this genome-wide data, because currently this is called genome surveillance, right? Because currently the data about drug resistance in most cases we have is RIF resistance, right? Maybe INS resistance. But we will see in the data that even if a patient is RIF and INS sensitive, they are still resistant to many other antibiotic, including the final, resort antibiotic. So those are still spreading, in the community, unknown. So we need to really figure out how exactly these drug resistance patterns and combinations of drug resistance are spread throughout in India, to actually develop a proper strategy to fight this problem, to actually make India TB Mukt. So that's what we are planning to give the country. One is the countrywide DR mutation map of M tuberculosis, which is essential requirement to strategize the TB elimination program. So I'll talk about it a little bit detail later. And another important thing is, even if we know this, right, that there are a lot of money spent on research worldwide for tuberculosis research. We still don't have a good vaccine. We still don't have, we have to keep continuing making new antibiotics as well, to actually, fight emerging drug resistance and all those aspects. So to achieve that, we really need the reagents or the resources to work with. So if you look at almost any, TB laboratory in anywhere in the world, almost everybody works. Most of the work is done on a single strain, H37RV, which is a reference strain. But that's not enough, right? Because you have tons of, every isolate is different. So at least we need to have representative isolates that is spread across the country, to actually meaningfully develop a new drug, or even to develop a drug candidate. If we may have a very good drug candidate, how are there variations in that gene? How would that affect the immunity, immune response? All these things we need to really have an idea. This is not something one particular group can address, right? No one group can address this, but we need to have these resources fully characterized with the genome sequence out there, so that any researcher has full access to that, they can pick it up and they can work on it. So that is what this project is supposed to deliver to the country. And this is the basic pipeline that I talked about. I'll just skip this. Quickly go through that. And ICMR, NIRT also contribute quite significantly to this program. So the clinical samples are sent to ICGB, where it is put into a repository, then genome sequencing and AML model, those are done. As of today, we have close to 25,000 genome sequenced and analyzed. The national biobank strength is around close to 12,000, which is amazing. Right? No one else has. This is probably 100 times bigger than any other available repository for clinical isolates. And we also have the metadata of a large number of patients here. Right now, this is not reached that particular number, but it's growing. We have methodically, and this is available on the portal as well. Anybody who want to look at the data, this is available on the portal as well. And yeah, so we have collected samples from throughout India. Of course, you see there are some gaps here and there because of sampling. The site we may not have in some places, but we need to fill all these gaps, and we need to reach the final number. And another important thing is the genome sequence quality. So we make sure that these are all processed using exactly same pipeline with the DNA isolated from one center, to make sure that you have very high quality data out there with median 9.5 million reads, which is very good for any bacteria mapping, and the quality levels are also extremely high for these samples. And now, if you to give an overview of what we see, if you look at it. So now we have the whole genome data with us. We can clearly have an idea about how different lineages of tuberculosis is spread all across India. And this is important because different lineages show different disease severity, different levels of drug resistance. So how they are spread across the country is extremely important to understand. And we do see that the lineages, one, which is a blue in color, that is highly predominant in the southern part of India, especially Tamil Nadu, Kerala. If you go to West India, like Maharashtra and Northern India, it's actually the lineage uh, 3 that is much more, the yellow color, that is much more predominant. So, yeah, but even Telangana or Karnataka, you can see much higher numbers of lineage 3 compared to lineage 1. Now, we also, another important aspect is it's not always a patient is coming with the tuberculosis. It doesn't mean that that patient is infected with just one strain or one lineage, right? You can have mixed infections. Same patient is infected with two types of tuberculosis, which have genetic diversity. And that's a big problem which in treating, because one may be resistant, one may be sensitive. So, how you decide the treatment, that's a big issue that in the next talk, what we have found from this study, Dr. Dheeraj will talk about. And another important thing is the NTM, so the non-tuberculous mycobacterial species. So we do see quite a bit of them. No, not very. If you could compare the total numbers, it's not that very high. In our data set, we have M. bovis, M. oryges, and one case of M. capre. So by doing a genome analysis, we can also identify how these NTMs are distributed. Now, coming to the most important aspect, the drug resistance. Now, I have to clarify here. So here, our design is such that we take only new cases of TB. So we don't take tuberculosis patients who have relapsed, who had a history of previous treatment of tuberculosis. So we take only new tuberculosis patients and looking at them. And good thing is that in that we see that around 65% of them are sensitive to all the all the drugs we know about, the mutations we know about. That means around 35% are resistant, which is actually a high number. And among them, 25% are resistant to multiple drugs, more than one drugs. And around 11% is resistant to a single drug. So this is what we know. So we have quite a bit of resistance there, and majority of resistant strains carry mutations that make them resistant to multiple drugs. And the right-hand side is the how different antibiotics. I'm sorry, cannot really read the number of the antibiotics there, but the largest peaks are one is the streptomycin, that is the highest peak, and the second highest is the isoniazid, and the first one is rifampicin. So those are pretty high in the population. And the one in the red box, so that's actually really a red flag for us. Those are fluoroquinolones, which are primarily used as second line therapy, and we see quite a bit of resistant mutations in the fluoroquinolones. That's actually really something we need to be very careful about using those drugs, because that's part of the BPAL-M regimen that is used for MDR drugs. We are already resistant to that quite a bit. But other drugs like bedaquiline and all, we don't see that much of resistance, which is good. And now, if you look at how the resistance is distributed across different lineages, what this figure shows is that the blue bars, right, the middle, those are lineage 2. So we can clearly see that for each antibiotic, each bar is for an antibiotic. For almost all antibiotics, the blue bar is the highest. So that means the lineage 2, which is also called the Beijing lineage, or it's highly virulent, lineage. So that they show extreme high level of resistant mutations, and that is much more clear here. We can see if you look at the donut plot, the stacked donut plot here. The outermost circle, that shows the total number of samples by lineage, and it's colored by lineage. The red one is lineage 1 and the blue one is lineage 2. So you can see the lineage 2 is actually very less among the total samples. And the next inner circle shows MDR strains. Now you can see how the lineage 2 has expanded. So lineage 2 contributes maximum 10% of the samples, but 50% of MDR are contributed by lineage 2, and that is true in case of pre-XDR and XDR as well. Lineage 2 has extremely high occurrence of MDR and XDR mutations. That is something that we need to be careful about. And second thing is how these mutations correlate with each other. How mutations with different against different antibiotics correlate. That means if a strain has one mutation against resistant mutation for one antibiotic, how likely that it will have another mutation for another antibiotic. And we can clearly see that the top, these are two different aspects of that. The top left corner, those are the primary, the first line drugs. So if you have a first line drug resistant mutation, it's highly likely that you will have mutation in another first line drug. So that's something that really comes up. And of course, amikacin, kanamycin, caprimycin, they form a very strong cluster because they are of same class. So basically, the mutations are shared between them. So that is why they show as very, very, very blue. And this is probably one of the most important, slide I would say. Here, what we are trying to show is that the left corner, top left, that plot shows the strains that are INH sensitive and RIF sensitive. So normally in a clinic that is considered as a sensitive strain, and the first line drugs will be given if I'm not wrong. Okay, and if you look at the red box within that, those are pyrazinamide and ethambutol. Around 6 to 7% of patients, those who are sensitive to those two drugs, are actually resistant to the other two drugs that you're giving the patients. So that means we are actually unnecessarily giving those drugs to those patients because they are already resistant to that. But unless we have a test that can actually look at the resistant pattern for all these antibiotics, we are unnecessarily giving them these antibiotics. Probably the patient will be better off if we give another two antibiotics for them. And same is the case for the second one is RIF resistant, so that will be considered as I think MDR TB. And among them, we can see moxifloxacin, around 17% are resistant to moxifloxacin, which is bipalum resistant drug. And we see bedaquiline and pretomanid as well, some level of resistance. And this pattern continues throughout different combinations of these isolates, which we can classify as MDR, pre-XDR, and XDR. So the take home, what I want to say is that unless we know the overall pattern of the drug resistance, we may be giving antibiotics unnecessarily. So ideally, we need to have a personalized regimen rather than having a fixed regimen. A TNGS program to actually, as part of a primary diagnostic system, should be able to help us with it. And then this is how MDR and pre-XDR and XDR are distributed throughout the country. We see that though we have quite a bit of samples from South, the South has lower incidence of MDR and pre-XDR. The reason is it's predominantly the lineage 1 there, which has less of these mutations. And we see West, East, and Central regions have higher occurrence of MDR. That reflects the lineage difference within this. Now, another important aspect when it comes to genotypic DST is that you need to compare genotypic DST with the phenotypic DST. How do they fare well? How do they fare well compared to phenotypic DST? And they do. So they are very highly comparable. We do see that except the bottom left, if you see, most of the first one is resistant, total resistant. That is then from the genotypic testing, and the second the bar is true positive. That means those are considered found positive from phenotypic DST as well. And the third bar, the cyan bar, is false negative. So they are found in genotypic DST but not in phenotypic DST. We consider them as false negative or discrepancies. So if you overall, if you look at it, they both the genomic DST and phenotypic DST, they match with each other. But we do have, and yeah, this is another plot directly comparing genotypic and phenotypic DST patterns. They kind of overlap, almost completely overlapping, indicating that genotypic DST can indeed capture the actual drug resistance profile. But as we said, we do see quite a bit of discrepancies. So here RR, in the table, RR means first R is for phenotypic DST, second R is for genotypic DST. So they both match. So genotypic and phenotypic match. SS also, both of them match. But the third and fourth columns, which are RS, which is resistant in phenotypic and sensitive in genotypic. And the last column is sensitive in phenotypic but resistant in genotypic. Both are very interesting deviations. And that's probably where we can identify novel mutations and expand our understanding of drug resistance here. So Dr. Dheeraj will in a few minutes discuss more about that aspect. And to at least to address these differences, complement these differences with the baseline gene expression profile of these. So we don't have much data on the gene expression profile of these isolates. We have done a transcriptome analysis of these isolates as well. Around 80 we have done at this point, which has around 60 are from lineage 1 and 2 together. And one thing that we really find is the transcriptome changes, basal transcriptome changes are primarily driven by the lineage structure. Okay, so we can see the green one is lineage 1 and the bottom, the orange ones are lineage 2. So they drive most of the transcriptomic variants. And it's very interesting aspect is like lineage 2 is more virulent and more drug resistant lineage. And we can see that many of the virulence driving programs like metal handling, polyketrate synthase, even a lot of transcriptional regulators are upregulated in the lineage 2, while DNA repair damage genes are actually downregulated in lineage 2. So we are actually looking further into see whether these can tell us something about the differential virulence of these lineages. And with that, I will stop here. So to conclude, we have sequenced around 25,000 and growing number of clinical isolates of tuberculosis. We have a biorepository of around 12,000 isolates so far. We have generated a map of DR mutations in India, and we highlight the requirement of genomic UDST for MTB and personalized drug regimen. And we do acknowledge it's actually the flagship program for Department of Biotechnology, Government of India, of course with the help of ICMR and Central TB Division, and all the STOs and DTOs from wherever we got the samples, they all helped us to achieve this. And of course, the NTGS consortium members, who is a remarkable group to work with. And I'll stop here.
Thank you, Dr. Anish Kumar, for wonderful presentations. And it's really a very important area that you have opened up. Now we have been talking about precision medicine, personalized medicine. So you have given very overview of the importance of the genomic testing in diagnosing the resistant tuberculosis, and how it could strengthen and control prevention, management, and elimination of the tuberculosis. That is a very important thing. Now the approach you have shown, the genomic, that I think we're talking about the precision medicine, not the one fixed treatment protocol is for all. So we are looking for precision medicine due to probably the advancement of the AI and machine learning and everything coming up. So genomic sequencing is very important. This is a gold standard, no doubt about this. If you want to treat someone, we must know that whether we are abusing the ATT or we are misusing the ATT because we are not sure whether the person is having resistant or not resistant. If resistant, to which drug is resistant. And there is scientifically, there is no doubt that unnecessary we don't want to give the medicine which is not really going to work for this tubercular bacteria. And then in the beginning, we must hit with the correct drug, the correct regimen. That is our aim, and not that giving at the same time a fixed dose, and subsequently after a few months, then we suspect this patient is suffering from resistant TB because of not responding. That is what the suspicion comes, not as a really microbiological testing pathway, that we don't go for testing to look for, to search for the resistant is not the habit or the not in practice, that subsequent is a time frame manner, is a active monitoring system is not there to look for tuberculosis, resistant TB. Unless there is symptoms and signs not progressing as per the expectation, the patient is not responding better. But how to implement this? This is $1 million question. That's definitely we want it. This is the perfect way to treat the patient, and probably this is the way we can eliminate this tuberculosis from our country. But the question is how to implement this, our genomic testing policy. As of now, we discussed yesterday that, our TrueNet and CBNet and also all the machines are there supplied even into the sub-district level, and these are not used. There is no technology, a technician, and then also if it is there, no kit for testing. So we have some policy. Now, is it that it's a really brainstorming session how to really utilize this, the genomic and the gold standard, but at the same time, channelizing this process up to the grassroots level, up to the sub-district level, collecting the sample, transporting the sample, before that suspecting, when to suspect, who is going to really identify and detect, what is the mechanism of detection and sample collection. If someone is going to collect the sample, then only you will be able to test this. Genomic testing is not really possible at the sub-district level or any other. So transportation, and before that is suspect, how the patients are doing, what. So it is the real-time monitoring. So there are challenges, I think, but whatever you said, really this is the gold standard, the pathway for treating the patient, and therefore it is going to strengthen our elimination program. So thank you very much, and if you have quick questions from the audience, you can address. We'd like to have some comments.
Very nicely he has pointed out the the genomic study of but that has opened up a new complex area. As a clinician, I think how is it important, how I am going to use this information. Obviously this is the only the beginning, then we may reach the. I just compare it just like we are all Indians. I may be an Odia, you may be a Gujarati, he may be an Bengali, he may be an Bihari, but we are all Indians. That is, but question is, how does it differ? How a Bihari differs from an Odia, and how a Odia differs from Bengali? But we have all, we are all Indians. We have got a common path for everything. So I think it is similar to that. There are now every bacteria, every mycobacterium has a different way of expression. So how it is really going to be used in a clinical sense? Will have every patient, can I have a different type of regimen? Or everyone will have his own specific regimen? Is it possible? And how we are going to integrate, that is what is the now major question. We have understood many things, we gathered so much of data, but how it is going to be used clinically, that is will be the next challenge. And I am sure once we have got, we first understand what is happening, then only we can come out of some conclusions. So let us have some questions or clarifications from the audience.
And you also from a study, very important information have come up that the lineage 3, the East African Indian are the predominant, the group of the lineage, the tuberculosis that genetically involved, and also lineage 2 that you have shown that most of the cases are MDR are from the lineage 2. That's also very important information. So if you can get this is a lineage 2, so right from the beginning we can really know. So these are all this no resistant cases. And also now most of the time when we do not apply the specific no precision medicine or personalized medicine, we have a syndromic approach. So at present, I think we have a syndromic approach for treating tuberculosis. That yes, this is a fixed dose. You just diagnose TB and take this drug. So that's also one policy that we have. So how to integrate this genomic and then to strengthen for becoming a practice, to make a practice of personalized medicine. That's also in preparation. I think there are maybe one or two questions
I had one
expecting
question.
from the audience. Please.
Thank you, Dr. Nish, for giving us an overview of this NTGS study and some interesting results. So when we find a discordance in the phenotypic and genotypic DSD, what is your suggestion about which should be the reference standard and how we should treat those patients?
Okay, so I think if, like in some case of drugs, I think it's a pyrazinamide or some of the drugs, I can't recollect the name, the phenotypic DST is not really reliable. Right. In such cases, definitely genomic testing will be a lot better. And in other cases, we don't really see much of a difference. If you look at the graph also, you can see that only 2 drugs which shows quite a bit of difference between them. In such cases, it's well documented that they don't really respond well in phenotypic DST. So I think going with the genotypic DST alone will capture probably the more than 95% of the actual cases, and that will be quite remarkable. And of course, that we have to continually monitoring it to make sure that they respond to the drugs given by based on the genotypic DST.
You have one slide you have seen that there is a 35% resistance, genomic resistance. But what is the country's level? I think around 2%.
What is that?
Country's in India's resistance, drug resistance, MDR, I think around 2%.
Right.
So 2% and 35%, I think it's a big gap.
So that's what we don't want to. That's what this is. Yeah, good. Thanks for asking that question. We don't want to highlight it as a country's general statistic because see, this is a genomic study, and the sample collection was not really uniform throughout the country. Of course, depending on the centers, there was local, concentration of sample collection. So those things would, like for example, a lot of samples come from Bombay, which is well known to have a lot of drug-resistant TB and very high levels of, the lineage 2 there, and some of these cities, right? So they may have skewed some of these results. So the idea here is not to project, not to imply that these numbers really reflect the overall Indian, resistance burden, but this is primarily to address the genome diversity as much as possible, and we hope it should be continued process to actually reach the same density throughout the country, so that we can actually at some point, use this as a, you will get the same number as the based on the other tests that we'll have seen.
I think
I have
also, one more thing is we have, when we call something as drug resistant, we are looking at all the mutations at the same time.
Yeah.
But many other, strategies used for classifying MDR and other resistance, they don't look at all of these drugs, right? It's mostly based on the TrueNAT or CBNAT, those kind of tests. So that also may change the actual numbers that come up with. But we are not saying that this is the actual prevalence per se.
But actual prevalence will be maybe 5%, 10% difference.
could be.
It will not be 2% definitely. So that is why targeted.
If I may add to
So
what
I think if you do this to nationwide level, probably we'll come to a that particular number. But right now we cannot really make it.
if I may add to the
that
answer.
that means we are going to treat all MDR cases, selected MDR cases, like you treat as a lung cancer. Means it's a treatment of choice is genome according to the genetic changes. That means genome testing. So I think that's more important. Dr. Bhajan, you want to-
That's why genomic testing becomes important.
Dr. Anish, I just wanted
Yes,
to add.
I
some-
just want to add what Madam had asked. Just add to your response. What you answered, like what you responded, is absolutely correct. To add to that, phenotypic resistance can also happen. Can also detect the heteroresistance, which is not detected by the genotypic one. At the same time, the genotypic resistance can be detected, detect the mutation, which actually may not be conferring the resistance.
Absolutely.
So those things also should be taken into consideration.
Yes.
To compare between phenotypic and genotypic, outrightly we cannot say that
I agree with
genotypic
that.
is.
Yeah. No, I'm talking. Yeah, I absolutely
Yeah.
right. So
And for that, I think WHO has come up with a manual, the catalog, where which all mutation confers to the risk. So
yeah,
those
we use that
yeah,
list. We
yeah,
actually
right.
follow the WHO
So
list.
those things are very meticulously to be taken into consideration and analyzed.
So all our mutation predictions are based on the WHO list of confirmed, not really on the interim list,
Exactly.
actual confirmed resistant mutations. And second thing is that when we talk about the actual phenotypic DST for all these drugs are done in very few places in a very, not really as part of a program or at a wider level, right? So we are actually comparing, we should be comparing with the what is normally happening, which is GeneXpert versus if we adopt something like a TNGS. That's something that we need to really compare. Not exactly the phenotypic DST. Phenotypic DST for 14 drugs is much more expensive than doing a TNGS also.
Expensive and very stringent
Exactly.
technology also is
So
required. So everything has to be like weighed in a very balanced.
Absolutely. So using a TNGS or that kind of test will take our success rate to much higher than based on GeneXpert or TrueNAT, that kind of. That's the whole point.
Definitely.
Sir, just I have a quick observation from this. Now, you have projected the MDR tuberculosis is 24%.
Not, multiple drugs, not
My,
India.
multiple drug resistance is 24% and mono resistant is 11%
Right.
out of your this.
Right.
So total it comes about 35%.
Right.
Now 35% are resistant and most of 24% are multi-drug resistance.
Multiple, yeah.
Multiple
Four
drug
years,
resistant.
yeah.
So if we consider, and that these are from the patients, definitely that under treatment. But if we talk about the mutation and not clinically significant, as we say that about the clinically, we detect all over India 2% about the drug resistant that we are thinking in that way, clinician, if they are to treat the patient.
Right.
Now we are giving a shocking information that 35% are resistant and based on mutation. And at the same time, we're talking this mutation may not be clinically relevant. Am I right? Because they may not be really real resistant, because mutation may not all the time real resistant and to the drugs and may not be. So it's a huge understanding gap in between 2% and 35%.
Right.
And if you go for testing and you give the mutation, this is a multi-drug resistant TB, then a regimen will be shifted towards a different tough regimen. Now, at the same time, we talk this may not be relevant. So how we are going to?
Yeah. So
Dr. Anish,
my
can I add
take on it is, the 2% versus 30% is a wrong comparison, because of, as I said, the skewness of the sample collection per se. Because
25,000 is a
Can I
quite
add
huge
something
number.
to that, Dr.
it's a
Anish?
huge number, but still we have skewness. This is a lot of it is, spread in around the places where we have.
Dr. Anish, can I add something? Sorry to interrupt you. I just wanted to bring in one point here because there was some confusion about the prevalence. So in INTIGS, our sample collection was basically from the intermediate reference laboratories. And intermediate reference laboratories, we know samples they get are from the PHCs and other health facilities where they suspect DRTB and therefore they send those samples for. So where the samples are sent to IRL when DRTB is suspected. So therefore what we find here, the aim of INTIGS project was not to find the prevalence of DRTB. For that we had a prevalence survey. The aim was to find the pattern of resistance. And the pattern of resistance we can do when we get samples which are most likely to be having resistant TB. So that is why our sample was not a representative sample of all TB patients in the country. So that is the first thing I wanted to point out. So please don't think that we are telling that the prevalence of DRTB, MDR-TB is 35%. This is the proportion of DRTB in our sample, which was basically from the intermediate reference laboratories. And what we project here, more importantly, is the pattern of resistance. That pattern would remain, applicable to all resistant TB across the country, except few states which we do not get samples from. Otherwise, this is the pattern that will be going to be present in DRTB cases across the country. So
I think now the message. I think the message is now clear that the samples which are collected from the patient are suspected for the resistant. So likely to have a high percent of resistant cases recording is not a generalized population and not the sample from the community and all. Absolutely. That's true. That's the message.
You see, that may not be entirely correct. You see, I think yesterday I hinted at the drug resistance survey in the country, which was done about 10 years back. That was a phenotypic study. And it was both, here also you told they are both the new cases and previously treated cases. That is why your sample collection.
Only new cases we have.
Only new cases you have done. They are the suspected cases. Yes, it is all right. So you have to tell what type of sample you have collected. That will be varying accordingly. Right. The second point is, the getting the multiple resistance. You are not talking of MDR-TB here. MDR-TB part is very clear. Yeah. There MDR-TB by definition, what we define, it is either rifampicin or rifampicin and INH. Exactly. So in addition to that, so we are not talking about those. In addition to that, there is resistance to other drugs. Exactly. So their clinical significance is not much as a clinic. That's what I am repeatedly telling. So there may be, it is all right, there may be additional, say for example, pyrazinamide resistance. So we are not giving pyrazinamide in them, or even if we are giving, at best we are giving one additional drug. So no harm. The real drugs which are already given, they are taking care of. So what is the clinical relevance is entirely different than what we are observing, and very rightly which is emphasized time and again, the mutation is not same as resistance. That we have to understand. That has to be clarified from the very beginning.
Right, but in most of these mutations actually do, if you do a phenotypic DST on them, they do match very well. We have done for a bunch of samples, we have done MIC studies as well. Yeah. You want to clarify something?
Is it working? Is it working? So actually what Dr. Anish just answered a little while ago, the phenotypic DST is not the reference standard. That is what I understand from the microbiologists also. So often when they get a result of pyrazinamide susceptible in the phenotypic DST, but the genotypic says resistance, then the genotypic DST is what the clinicians would depend upon for treatment. That is what I just wanted to add, sir. So it does have clinical relevance, not that we know phenotypic results and that is the gold standard.
I think due to lack of time and later on, I think maybe in the tea break, other questions may be addressed.
Very quickly, sir.
Yeah.
Since you are also on the dais and he is also there, how can NII be a collaborator with AIIMS Bhubaneswar if something has to be developed here in the eastern region? Of course, RMRC is there, but AIIMS Bhubaneswar also, if they have a team to begin some collaboration, what is a suggestion or pathway from your side as NII as a collaborator?
So we have now a strong, base in genomics. Especially, we are also trying to develop a TNGS kit as well. But genomic and the data analysis part of TB genome, we have with this project we have developed quite a bit of strength in that. So in that way, we can really work together to really take any action forward in that aspect.
I think, thank you that we can plan about the collaboration. That's a very wonderful, I think, proposition. I think, thank you, Dr. Anish Kumar. Thank you very much.
Thank you.
Now I request Dr. Brera for inviting the second speaker.
Yeah, I think it is my pleasure to invite Dr. Dheeraj Kumar for his talk, and I think we'll get more clarification, more clarity, and some more information. Because the dilemma always will be when we are gathering so much of data, how a clinician is going to utilize that, how the program is going to generalize it. As I was just talking to Professor Biswas, the question is, we have got 28 lakhs of patients. Do you think I will be having the genomic study of everybody and then try to develop a regimen for every patient? It is just not possible. The knowledge is different, science is different, and the practicability also will be different. As a clinician, that will be my dilemma. So please, Dr. Dheeraj.
Thank you. Thank you very much, chairs. And thanks, Anis, for setting the platform. We understand the huge gap between practicality and the knowledge that is emerging. But I think once we have the clear picture of, the problem, probably the gap can be filled. And that's the motive that drives us to get into more detail of the problems that we face. And that's why I changed the title of my talk to Layers of Complexities in TB-DST, mostly keeping in mind observations from the clinicians' talk yesterday. I just gave some clues to Gemini, the problems that we are, trying to overcome using UDST. You have unconfirmed diagnostics, you have unconfirmed drug resistance, treatment failures, emergence of drug resistance. So there are, a lot of problems, which the clinicians face day to day. And there is always a question, for a seasoned clinician that you don't know what to do, and we had discussions that sometimes you have to shoot in the dark, right? So as a basic science perspective, what we started into getting is that can you get some clues which start slowly but steadily filling the gap between what we know and what should be done, what is practically feasible. I can be at sometimes be very provocative in terms of what all should be done to actually address the problem that we face in diagnostics and personalized therapeutics. But that provocation is purely based on understanding that we have kind of evolved through the ongoing program. And it is probably with the clinicians to decide how it can be taken forward if something can be worked out in terms of feasibility, practicality. So Anish gave a wonderful background of the INTEGS program, which is a whole genome sequencing of MTB clinical isolates. We started to do 32,000. There are multiple sites as shown here. From clinical sites comes to ICGEB, where we get DNA to ensure the uniformity every time, DNA isolation, and then it is sent to clinical sites, CCMB and NIBMG, and sometimes to NI for DNA sequencing. And we also have developed the strain repository here at ICGEB. And eventually, NI has done all the analysis, AIML, and of course, different people pitched in even at analysis front. We had CCMB team helping in analysis. This is the current status. We have received around 25,000 samples. Almost 12,000 are there in the repository. They are well characterized now. And it has even helped in our INTEGS program, as I will talk in a few slides from now. that how it is helping us in addressing some of the questions which probably you can imagine that even difficult to ask, but we have managed to address those questions using this biorepository. And I will quickly jump to one of the slides that Anish showed about the discordance between phenotypic DST and genotypic DST. And we focus on only these two circles, the blue and red, where in first case the samples were phenotypically resistant, but there was no classic mutations as characterized by WHO gene profile was found in those samples. And the other one, which were phenotypically sensitive, but they had classic mutations which are reported by WHO to associate with drug resistance, simply signifying that both these approaches standalone may not be sufficient to correctly point out the nature of drug resistance in a given sample, right? And that could also contribute to poor prognosis because you don't know to begin with what is a drug resistance profile to define a regime that should be given to a given patient. So that's where we started thinking of, once we saw the discordance, we started thinking of how to utilize the biobank that we have developed in ICGEP. This eventually will reach to 25,000 or 30,000 is what our target is. This part is lagged because we focused more on DNA extraction rather than developing the biorepository. So what we actually started was doing MIC analysis for around 1600 samples for which we had phenotypic DST and the whole genome sequence and genotypic DST. And this is a sensititer plate which is available commercially. And what it has is for 12 drugs, they're added into each well with serial dilutions twofold. And you can actually figure out at what concentration of drug bacterial growth is inhibited, and you will know the MIC. And you can add a certain number of bacteria to these plates and monitor the bacterial growth over 4 weeks to see how the resistance is evolving or whether the samples were resistant or not. It took us some time to standardize this protocol, and just one of the representative example is what I'm showing here. So what was done here, so in most cases, you have the lowest drug concentration at the bottom, and as you go up, there is twofold increase in drug concentration, and these are the drugs, you have Oflox, Moxie, Diff, Amikacin, Steps, all those drugs are there in this. And this is at the end of 4 weeks of, every week you take the picture to see that where you are seeing the growth, where not seeing the growth. And what we started doing towards the end is we also started doing LMR assay just to get a very clean black and white picture or pink and blue picture as this LMR assay gives you to see where exactly the growth is inhibited at what concentration of drug. Now, this analysis gave us something even more perplexing, and that led us to more questions, but I'll begin with what we observed. This is one of the strain which is in TGS ID 1368. These are all mostly from Hinduja because phenotypic data is available only from Hinduja as of now. And what you see is that, sorry if I can see the pointer. Yeah. So week 1, this has certain MIC, which is again, it is resistant. But by week 2, week 3, week 4, it has become highly resistant. So MIC has increased from somewhere around 4 to 16 for this particular strain. For Moxie, week 1 it was sensitive, but week 2, 3, 4 it has become resistant. Amikacin, and what is written here, RR means it is phenotypically resistant, genotypically resistant. But this is the pattern we are seeing. Amikacin, it is phenotypically and genotypically both sensitive, but right from week 1 you are seeing very high MIC. So it is resistance to begin with, right? It's not matching either phenotypic or genotypic DST prediction. Just another example. I'll show just 1 or 2 examples to kind of give the message. MOXIE SS means again sensitive in both ways, but it is higher than the MIC. RIF SS, and you see here, first 3 weeks, it actually remains sensitive. But by the time you reach week 4, it has started showing resistance. And now we always have this control to ensure that this growth at the end of 4th week is not because drug has degraded, because the control wells you don't see growth, you know that there is no bacteria, it's not a problem of drug. And what you see is that there is one level of discordance that was coming between phenotypic DST and genotypic DST. The next level of complexity is arising because when you do MIC, it doesn't match any of those in many cases. I'm not saying all the cases, but in many cases it was not matched. And I actually picked up those cases where it is showing very severe discordance. And this is another example, again showing the same. You can see this one INH-RR cases. So it is predicted resistant in both, but it starts with very low MIC, but then MIC increases over time. Why MIC should increase over time? And that's what the question that we have. And it takes me back to some very hypothetical scenario that we had discussed, that how drug resistance emerges, and people used to think in many other bacterial infections it happens that during the course of treatment it acquires mutation, which not always true for TB, which is a very slow growing bacteria, and acquiring mutation during the course of treatment, we don't know. But what certainly can happen is enrichment of a very small fraction of bacteria which carries the resistance, has drug resistance phenotype, but is completely outnumbered to begin with. And over time, when you start treating with the drugs, the sensitive ones are cleared off, and you basically are enriching the drug resistant bacteria over time. Can you test that based on the samples that we have? We are seeing a phenotype which is kind of reflecting this event to happening. Can you test that? And we decided to actually test that. And we picked up few samples which were showing this discordance and time-dependent changes in MIC. And we followed on this same sensitizer plate. One part of it was taken for RNA-seq, and the samples which were kept on these plates for 3 to 4 weeks, we collected the bacterial growth happening just below the MIC level and did DNA isolation and sequencing analysis from those. So what I'm showing here is that if you can see, here is the blue color appearing. You extracted DNA from this well, this well. So where you have bacterial growth, after which there is no bacterial growth at higher drug, you pick out the bacterial palette and then do the genomic DNA extraction and isolation. And then you also have the inoculum stage DNA, which tells you where there is no drug exposure, what was the DNA composition there. And then of course the analysis was done. And right now this analysis only talks about the lineages, that what happened to lineage of those 10 isolates which were kept on this plate for 3 to 4 weeks. And this analysis was done in CCMB. Jagdish did this analysis. And I can quickly give you the clue about the colors. So different color reflect a different lineage. So green color is lineage 2, blue color is lineage 1, orange is mixture of lineage 1 and 2 both, red is mixture of lineage 2 and 3. What you see, the first column is written ND. So that is the DNA analysis before the drug, the strain was exposed to drug. So there is no drug. This is the basic composition. And they are predominantly of, let's say these are lineage 2, this is lineage 3, again this is lineage 1, 2, and like that. This one was mixed right to begin with. And then the subsequent columns actually tells you what was the predominant lineage when they were selected on amikacin, ethambutol, isoniazid, rifampicin, or streptomycin. So all these drug names are written here. And what you see is that while in some cases lineage remain constant, there are cases like 1692, which was susceptible to begin with. It has lineage 3 to start with. But when you select it on amikacin or ethambutol, at the end of 3 weeks' time, the DNA sequence, when you analyze, what you see is that it is enriched with lineage 2 and 3. And what it tells you, again, the mixed lineage. Next strain, which was mixed right to begin with, which retains the same composition if you select on ethionamide and isoniazid, but the moment you have RIF, it acquires a different lineage, lineage 2, right? And something similar here. So what is happening is that you have the primary samples which are mixture of different lineages, and some drug resistance are being carried by one lineage but not by other, and you are enriching those over time if you treat them. Now imagine this is happening on the plate. If this is from a patient, so you start them in HREJ at the end of 4 to 6 weeks when all the sensitive ones are cleared, you have actually enriched the resistant bacteria there, and that kind of emerges as a DR cases at the end of 2 weeks and at 2 months, and we say that okay, this is a treatment failure and probably something happened to those patients. After seeing this, we went back and did the analysis for all the 1600 sample for which genotypic and phenotypic DST was available to look for what is the composition of lineage, mixed lineage. And when you do the mixed lineage analysis, the genomics analysis is, a lot of statistics there, right? So you can think of if there is 1% sequence differences are coming, you will just ignore it. Or people generally take 10% as the threshold. You ignore it anything less than 10% as probably an artifact of sequencing reaction. But what you miss out in doing that, if let's say the mixture was 99 to 1%, right, of two different strains, then you will kind of ignore it saying that it is an artifact, but actually that's the information which we are throwing out in the dustbin. So what you see here is that most of the discordant samples, discordance means where PDST and GDST did not match, were actually from the mixed lineage. So they had mixed infection. They had from any two categories, lineage 1, 2, 2, 3, 3, 4, like that. And the analysis so far is done only for lineage. Imagine even within same lineage, if there are mixed strains, two different strains, one carrying bacteria with drug resistance, one with not. If that happens, probably the mixed infection will contribute to almost 90% of discordant samples that we will have. And that's huge number. Even if you go by the numbers that Anish showed for PDST, GDST differences, that still is a significant number. So that is something which really very strongly came out of this. And then this analysis actually Anish did. This is for all the MIC analysis that was done, and he did the breakpoint analysis. And what you see is that they do follow the observed resistance pattern. So those which were RR have very high median for MIC or drug resistance. RS has slightly lower, SR is slightly lower, and SS is lower. But if you look at the spread, even in the SS group, you have, SS means those which are sensitive both phenotypically and genotypically. You have strains which have very high MIC level, meaning that PDST, GDST together also is not able to capture the true picture of resistance that is available or that is prevailing in the patients in general. What are the inferences and implications? What I just said, that PDST and GDST alone or together still do not capture all drug resistant cases. And there is a very high level of uncertainty in predicting the true resistance pattern. And you all agree when the standard is to go by RIF resistance, and he showed you in one of the data that how many RIF sensitive strains also had resistant to many other drugs. While RIF resistance is a sure short way to identify DR cases, there is no denying that. But RIF sensitivity is not a sure short method to identify all the sensitive cases, because, and probably those are the cases which gives true failed treatment outcome. You cannot do MIC for all samples and all drugs. It's impractical, not feasible, difficult. I mean, you can put as many phrases of very similar nature, but that's what it is. Can we capture all variations that together predict 100% of drug resistant cases? It looks very difficult as of now. because we have been going by very standard set. I remember people used to talk about just hotspots several years now. Nobody talks about hotspots because we started seeing many other mutational sites where they can contribute to drug resistance. And then develop tools where you can do targeted NGS to cover all those sites where you've identified mutation. Let that be many more sites. This can be the UDST in the truest sense, where you can actually capture all those mutations and you are very sure that when you are saying that this is sensitive, that person is sensitive actually and will respond to all 4 drugs that you begin with. This is challenging and looks very difficult to achieve, a gap which requires a lot of brainstorming from the clinical side who can really come up with. But from the basic side, to actually able to identify everything that contributes to drug resistance. Since we have now well characterized 25,000 sequence data, which will very soon reach to 32,000, we have done GWAS analysis, and this is something which is ongoing. So we don't have clear outcome from this data. But what you do see is that the standard mutations that is associated with a drug resistance, for example, isoniazid, you will get CATG and INHA mutation, you do find those. But then you also find a lot of novel mutations. How do you associate those with clear pattern of yes or no, whether it is contributing to drug resistance or not? Number one. Secondly, whether it is contributing to MIC changes, because resistance are of many kind, as I saw in the MIC plate. So someone is at just 2x MIC considered as resistant, but there are others which are at 16x MIC. Now 2x MIC and 16x MIC may have different genomic backgrounds, and that's why they are behaving like that. So can you identify that? And treating 2x MIC versus 16x MIC, can you work out a strategy to address this? So of course we have identified novel mutations across RIF and INH, and other drugs are being analyzed and that will be verified. So the wild thought, and we were discussing yesterday with Anish regarding this, this mixed lineage infection during UDST, if we are able to establish that, we have tried doing it with sputum sample directly, that needs little more standardization. But if you do that, you not only identify all the mutations, you can also identify mixed lineage infection. If you can include a probe that tells you about the lineage, and you will know right in the beginning that there is a mixed lineage, and you have probably high chance of something going towards treatment failure. The second thought was even more provocative, and that's what I had begun with. Can you have dynamic therapeutic regime? And Professor Behra was very, practically told us that even for every person, having a personalized treatment regime is very difficult considering the patient burden in India. And I'm talking about dynamic therapeutic regime, where based on UDST and mixed lineage infection, if you know to begin with, you have first 6 to 8 weeks, one set of drugs like HREJ, if they are 99% sensitive to that, but 1% they are RIF and INH resistance, then change the regime after 2 months and bring additional drugs. That can be any drug based on whatever you already know from the UDST profile. So, I know there are practical concerns, feasibility concerns, but this is food for thought. Unless we start thinking, we cannot take a step towards that. So, finally, in last 2 slides, we have this INTGS biorepository. We have developed a protocol that anyone within India can actually have access to samples from this repository. Of course, this is a BSL-3 material, so it requires regulatory guidelines, but they all are in place, and we will very soon open the site for starting accepting requests for giving TB isolates of defined nature. You can go to the INTGS website, see what mutation, what drug resistance patterns you are looking for, and you can identify the clinical sample ID, and then you can request for that particular ID, and that will be made available. And that can be used for many purposes, basic research. And if you have a diagnostic kit that you have developed, if you want to test it, you have a ready reference of thousands of samples. You can come to test on those samples to verify that your test that you have developed is really working. so these are the different applications for this. Can be true for both academic setup and for the industry setup. So I'll stop here. I will not re-emphasize on the need of UDST and targeted NGS that actually has to evolve, even if it starts at a pilot scale, but will set the platform for taking it nationwide and contributing to TB Mukt Bharat. So I'll stop here. Thank people, thank funders and the NTGS consortium partner. Very wonderful team. So happy to work with all the clinical and research labs. Thank you very much. We'll happy to take any question.
So thank you, Dr. Dheeraj. You have at least clarified some points. See, I had just one question. Do you have got the clinical data of all those samples of the what happened, what drug regimen was given to them?
Exactly. So I think the clinical team so far has been collating all the metadata from Nikshay portal, and it's such a challenge.
Yeah,
While
I know.
Nikshay is something, TB is notifiable disease, everything goes to Nikshay portal, but all the information are not always fed by the the person who are acquiring the metadata. So we would love to have the treatment outcome information from the Nikshay portal. For those 1600, it will be fantastic to have that.
Yes.
So we are trying to get that information through, of course, our clinical, collaborators. Once we have that, you can have very clear observation to clinical outcome that these are the, discordant ones which you identify experimentally are the ones, some of who actually fail treatment, right? So once you reach that conclusion, that is phenomenal, and that also gives you very strong justification that why you need to really go towards the direction that we are thinking at this stage.
I think you are very right. That is very, very important. Just gathering, as I always saying that gathering lot of data does not mean anything unless it has got a meaning. The same thing, Professor Biswas, and then if you are planning I think you should plan it that way. What happens, you do every, whatever is required, you should get all types of information. If you are planning to have your collaborative project here, you should take all these things into account. Because what does it mean? That is always the question. Ultimately, what does it mean? So what? That is the question. So how does it help? Okay.
I think this is the gaps that the labs and the gaps is in between the clinical field and then all the genomic studies and molecular studies.
Yeah.
So I think we need to have a collaboration, the clinical scientist and the molecular scientist together to address these challenges. Definitely we'll go for it, and we're planning for that. Thank you very much.
Absolutely.
Thank you.
Thank you so much.
And any questions from
Sir,
audience? Quick questions,
sir,
maybe one or two,
I-
as we are lacking short of time.
Sir, I agree with you that there is a lot of molecular advancement, molecular research, but really clinical application, filling the gap is that big gap. So that need to be applied in clinical field. Unless we have a clinical application, then where you stand? That is one issue. Regarding targeted treatment, I just use search in Google number of lung cancer cases in India, and search lung cancer number of MDI TB in India. Luckily, it comes 110,000. You can search now. If we are, I mean Dr. Behra and myself, we are treating both lung cancers, and also we are looking after, my colleague is looking after tuberculosis, but what I mean to say, if the target is used for lung cancer, why you cannot use in TB? The reason is, lung cancer is not going to spread, but if you do leave a chance of not treating a TB, you are creating a misfortune for others. So it is, TB is going to spread others, but lung cancer is not going to spread others. So it should be more harsh, more accurate, more targeted, and more aggressive treatment. I mean that unless we really do it, I mean we cannot control tuberculosis, real sense.
Absolutely. Really, thank you for this Cancer Connect, because a lot of, at the policy making side, people, get more worked up when they hear cancer than they hear TB. So I think a lot of us here.
Sir, I want to say that a few years, when starting from the AIMS, we have treated more than 3,000, my department treated more than 3,000 lung cancer cases. I mean, so look, treatment, we need, so it is, we get more of lung cancer cases. If regarding admission, TB cases are definitely coming, but this is not no, not the hospital for tuberculosis treatment,
Right.
but diagnose and get treated. But
Yeah.
it's look at, I think 80% beds of our department is occupied by lung cancer with some complications. Do not admit lung cancer because ordinarily.
Thank you.
Thank-
I think there is no doubt about practicing the precision medicine nowadays. We, with the advancement of the all artificial intelligence and genomics and all, everybody is looking for precision medicine, and it's not for tuberculosis, but it is for applicable for other diseases too. It's not on one antibiotic is really responding to respond for all. We need to understand many things, proteomics, genomics, and various other omics to prescribe which drug is really fit for which.
So
So,
actually, if I can add, so
yes,
if we
please.
may bring in many omics, then we will get more confused. But if we continue focusing on genomics, that alone has huge potential to bridge the gap in terms of how many cases fall off the basket. So you can actually ensure that majority of them, if not 100%, you will have majority of them actually captured and treated. Because yesterday, Professor Behra was showing number of cases identified, 70%. Out of those actually get it treated, 40%. So actually you are treating just 30% of people, 30 to 40%.
I think that is our challenge here. That is exclusively we are focused on this conclave is for this, how really we can explore the window to implement this genomics into the field for really giving the treatment specific and very correct treatment at the right time, the right dose and right treatment protocol. So I think thank you very much.
Thank you.
Thank you for giving a very excellent deliberation.
Thanks,
Thank you.
Thanks.
I thank both our speakers as well as our chairpersons for an insightful and thought-provoking discussion. So may I just ask you to stay back for the felicitation, sir, for a second. I request both our speakers of the session to grace the dais. May I now request our chairperson of the session, Padma Shri Dr. Digamba Behra sir, to felicitate our speaker, Dr. G. Anish Kumar Arimbaseri sir. Thank you, sir. May I now request our esteemed Executive Director, sir, to felicitate our speaker, Dr. Dheeraj Kumar, sir. May I now request our organizing chairman of this conclave, Dr. P.R. Mohapatra, sir, to felicitate Padma Shri Professor Dr. Digamba Behra, sir. Thank you so much, sir. Now I request everyone to disperse for a short tea break, and we shall reconvene in the same hall exactly at 10:15 a.m. Thank you so much.